And one of the first things that I always start with when I show some work is the team. So I'd like to acknowledge, these incredible people that I work with. All of our work is collaborative, and these people, both individually and collectively, literally bring it to life. So I'm going to start with a little bit of a framework here that I have, which is that I believe that buildings are living organisms. They breathe and they pulse. They're dynamic systems rather than static objects. And they involve more time and space than we typically consider. This is something Jasmine was just describing. So, in some sense, buildings start with the story of their materials and the desires of their inhabitants. And they end well beyond the day that they open and the photos are taken. Buildings include many sites of extraction, manufacturing, and waste far away from their own property lines. And buildings embody a wide range of species, technologies, and culture. So in this context, I'd like to describe today 6 different approaches to expanding the boundaries of architecture. In response to many global challenges that we're facing today, things like population growth, urbanization, and climate change, we've been exploring these different approaches as prototypes for scaling up to meet some of the challenges of our times. So the first approach I'm going to describe is managing complexity. So this approach involves a kind of hybrid of human creativity and computer automation to manage complexity. And sometimes some of the underlying technology for this approach is called generative design. And it's one way that I think we can expand the typical definition of the design of buildings. So some of our work in this approach, in this area, has involved a long-term collaboration with Airbus, the big airplane manufacturer. And Airbus, about 10 years ago when we started working with them, had this big goal. They were thinking far into the future of recreating, reinventing the way that we design and make airplanes. More specifically, they wanted to reduce the weight of airplanes, which would in turn reduce fuel consumption and carbon emissions. So it was a big goal, but we started with the way Airbus often does, with a demonstrator. And the idea was to prove out the big idea with something tangible. And we started with this part, airplane part shown in the red here. It's called a partition. It's the dividing wall between the seating area and the galley of a plane. And although it looks like a kind of boring and forgettable part, it's actually a difficult part to design to be both lightweight and strong with today's traditional engineering approaches. And so here, together with Airbus, we've developed an approach to explore thousands of different design options created with a different logic than typical human linear thinking, and to try to find the best options that would have the lowest weight and also the lowest displacement under structural load. So this was a kind of process of artificial evolution, sometimes called multi-objective optimization or generative design. And it basically involved a software system that generated, evaluated, and evolved literally dozens, hundreds, thousands of different design options, searching through the space for some designs that were both novel and interesting, but also high performing. And this was, in addition to a geometric approach, also a kind of data approach. So this is a different view of that same data. Every dot is a different design option. And you can see how there are a lot of different designs. You can use data analytics to sort through those designs, plot them on a graph in different ways, color code them according to their design over time, or according to things like their virtual DNA, what makes the type of design that they are. And eventually you can identify the mathematical set of best design options for meeting your 2 goals, lowest weight and lowest displacement under load. So you want to be at that 0, 0 point of the graph. You can't quite get there, but you can get things that are close and look at the trade-offs. So this was an idea of creating a new way of designing this airplane part. And we also wanted to test it out in the real world. So we actually built a full-scale partition We used metal 3D printing and a new alloy that Airbus had invented for this purpose, for making low weight airplane parts. We created a full-scale partition shown here, and it's currently undergoing a bunch of certification to fly in today's A320 planes. Here it is as a kind of test fit. So big ideas, some technology exploration, and the bottom line, though, is that if you look on the right, we were able to reduce the weight of this partition by about 45%, increase the strength by about 8% compared to the one on the left, the typical partition. This translates to less fuel consumption. This obviously saves money. But the real big picture thing is that it saves up to 1 million tons of carbon emissions per year if it's rolled out to all the A320s flying today. So I showed this because that was the starting point, but like many of our projects, they kind of develop and build into other lines of investigation and other projects. I'm sure like all of you in your own design work, this happens as well. So one way that happened for us was that after using this approach of computation to explore a wide space of possibilities. After using that for an airplane part, we then worked with Airbus to explore the same approach to design an airplane factory. And again, we used a real world example. This time it's the last unbuilt triangle of space on the Airbus campus in Hamburg, Germany. And instead of the previous example with the airplane part just having more or less 2 goals, you want to minimize weight, you want to minimize displacement under load, here we add 10 plus goals. And some of those goals were what you would think, you know, we call those operational goals, you want an efficient factory, but some of the goals were also financial goals, some goals were environmental goals, and some goals were even what you could consider social goals. We had some goals for things like employee work conditions. And the idea that we have here is that computation could be used not just for kind of cold-blooded efficiency and optimizing the things that are easy to optimize, but it could also be used to navigate trade-offs between many of the important but sometimes conflicting goals you have for a project. So in this case, we were trying to measure the easy things to measure, like daylight, but also the harder things to measure, like future expansion. You know, for every single factory design, which one was better or worse at being able to expand in the future to unknown forces? In other words, Airbus knew what they wanted to manufacture for the next 5 years, but beyond that, they might want to expand their factory, double the production of the airplane engines they're making, or they might want to transition that factory to be making something else, a different airplane part. So which layout is better or worse for the unknown for future expansion? Part of this data-driven process for architecture and for a factory was to do things like this. So this is a diagram of the floor plan of the factory. There are about 50 different production stations, about 200 different rules of things that need to be next to each other or near the exterior or the interior, or need to have a turning radius to get from one station to the other. And we tried to encode those rules in computation in the geometric model so that we could create different layouts, and for every layout measure how well it was performing for a number of different performance requirements. And then when we added the other goals, including the social goals I mentioned, we were able to explore a wide design space. So you'll recognize this is a little bit similar to exploring different partition designs. Here we're exploring different factory designs. Every design meets all of the requirements. In other words, it has all the required program space. It fits on the site. But different designs have different trade-offs. Some are better for environmental goals and worse for cost. Others are vice versa. Some are medium scores for environmental, social, performance, and cost. So which one do we choose? And that's a nice way to think that computation can actually enable human decision-making as opposed to replace it. So this approach then lends itself nicely to the rest of traditional design, combining, you know, the best of computation with the best of human creativity and imagination. It gives you kind of schematic design level floor plans, which you can then develop. We were also able to use some other aspects of computation, you know, once we were already in the computational model, for things like advanced airflow simulation through the building. So what's the best position of the windows and the skylights to get natural ventilation in the space, because this is a building that by requirement by Airbus needed to have no air conditioning, just natural cooling. There are a number of other things that we were able to do once we have this big data set of designs. Once you think of design as a data set, and this approach, which is slowly loading on the computer, is basically a way to take something like a 10-dimensional data set. Remember, I showed you 10 different goals for the project, some operational, some financial, et cetera. And you kind of compress that into 2 dimensions so you can start to try to understand it with your human mind. 10-dimensional data set's pretty hard to represent graphically, to understand with your mind, but there are ways to do it, including this approach of reducing the dimensions and grouping different designs. So we then think that this kind of approach shouldn't involve a sacrifice in how you normally make a good building, and we were able to continue to workshop the design to include a lot of things that we just thought were valuable for the project, a lot of sustainability features, but also a good place to work, balancing kind of human factors or human features, production goals for an efficient factory, some financial goals, of course, and basically creating a design that we thought made sense and that was designed to be constructed in the real world as a factory. So kind of using some experimental methods, but again, testing them out, in the real world with all of the friction of meeting the schedule, the deadlines, the budget, and, making it work. So approach number 2 is what I call drawing the environment. So this involves making visible some of the invisible but essential forces of buildings and architecture and cities, for that matter. So one way of thinking about this was that as we started to engage climate change more and more and sustainability and asking how we might design the environment, we realized very quickly that this was very related to how we might draw the environment. And this is a topic that we've been exploring at Columbia University in something called the Embodied Energy Pilot Project. Here's some drawings from it. And more or less, the premise of this project involves some things you probably know, but the total energy involved in buildings can be thought of as divided into operational energy and embodied energy. Operational energy is all of the energy required for operating the building, things like heating, cooling, ventilation, lighting, and anything you plug into the wall. Embodied energy, on the other hand, is all the energy required for materials. The sum of all the energy for extracting, transporting, manufacturing, and assembling materials or ingredients into buildings. And it's, we recognized as important that the percentage of energy in buildings that was embodied energy has been increasing over time. So this is an important but somewhat underexplored topic. Although we started this project in 2016, it's more and more recognized every year. So all this work about embodied carbon, exactly the same thing. We really need to think about that aspect of sustainability of buildings. So we set out to explore this topic of embodied energy through things like exhibitions, courses, a symposium, a book. And what I wanted to mention in the context of this idea of drawing the invisible and drawing the environment is that we started our analysis of embodied energy, as you might expect, through drawing data visualizations. So this particular drawing shows us graphically that buildings account for about 1/3 of global waste, energy consumption, and carbon emissions. And this other drawing, on the other hand, a different data visualization, shows us that embodied energy has been increasing over time. So you can see, not so long ago, in 1970, it might have been, the average was about 10%. 10% of the total energy in the building was embodied. These days, it's like 40%. Some people think it's higher. We also did this kind of visualization, like kind of comparison. So we're showing the breakdown of embodied energy by different materials, such as concrete or glass or aluminum. So each red box is a different material. You can see which ones are bigger or smaller. Here's a different breakdown by process. So where is all the embodied energy in different processes like extraction, transportation, or manufacturing? Yet another way to look at it is to compare specific buildings. So this is a really interesting study that compared a new timber tower to a 50-year-old concrete and steel tower. And you could see which one had more energy, more carbon, and you're kind of comparing by the building, not just by the material or the process. But really, we quickly realized that the data alone was not enough. Certainly it's important, but we also thought that we needed to start understanding the qualitative and relational aspects of embodied energy. So we moved from drawing data visualizations to drawing what we call material stories. The narrative of a material like concrete or wood or steel, from extraction to factory production to transportation to construction, showing it all in the same frame. Here's the material story of concrete. And basically the idea is that by drawing it, then we imagine it as something that we can design. So we're inviting ourselves to design the material supply chain, the sites of extraction, the process of factory production. So here's a material story for steel. We drew another one for wood. And we use this framework really to draw questions as much as we were drawing conclusions. So we drew a range of material formations and sites beyond what we would typically think of as the building or the territory of architectural design. So here's the site of a limestone quarry involved in concrete, which is involved in buildings. So let's draw it. The site of a cement silo, a building foundation, and the concrete structure of a building. For steel, here's a site for iron ore extraction, a steel former, container ship, a steel yard, and a steel structure. Same thing for wood. Here's the forest, a sawmill, a lumber yard, and the balloon frame structure of a building. So we think these drawings, these material stories, reveal something important about our buildings. They're a research model beyond the quantitative. They're not just analytical, but they can also be a tool for design. So they're not just representing what we already know, they're exploring what could be. And we think, finally, that this framework of embodied energy is not just an underexplored aspect of architecture, but it's also a lens through which we might see all kinds of invisible yet essential features of architecture, such as embodied water, embodied carbon, of course, and even things like embodied labor. The third approach is what we're calling design with uncertainty. So this is an approach that for me is closely related to design with biology. Design with biology really requires design with uncertainty. And one example of our design with biology recently, it's something that Jasmine already mentioned, is where we're using actual living organisms as tiny factories to help manufacture the physical stuff of architecture, the building blocks of architecture. And we sometimes call this biofabrication. So our first real exploration of this was almost 10 years ago now, it's hard to believe. And it started with an idea really about the Earth's carbon cycle, this endless loop of growth and decay and regrowth and transformation of carbon. And with the hypothesis, now this is somewhat known or encapsulated by thoughts about the circular economy. But when we were doing this, I was pretty early in circular economy thinking. This idea that instead of our typical approach, we could maybe borrow from the carbon cycle. So use as raw ingredients waste instead of high value materials. Spend a very small amount of energy and carbon converting the raw materials into building blocks. Then make a useful building, and then at the end of the useful life of that building, return all of the matter, all of that physical stuff back into the carbon cycle to resume the loop. So this was an interesting theory, but how did we actually try to experiment with it? It was through this actual living organism called mycelium. I'm sure you know about this organism. Here's some microscope videos of how it grows in these thin white filaments. It creates very interesting and complex patterns, kind of responding to the metabolism of the living organism. But in our case, we were interested less in the patterns and the form of mycelium and more in the function, because it turns out you can take mycelium, combine it with agricultural waste, not the high value part of agriculture, so like not corn kernels that could be used for food, but just the low value part, chopped up corn stalks. Combine those two things together, the corn stalks and the mycelium, and in about a week, it grows into a solid object. The mycelium fills in all of those voids within the loose material, and you get a solid object, which could be used for various functions. There's some great research on using this material for packaging because it has a property similar to styrofoam. And our thought was, well, maybe we can use this as a new kind of load-bearing architectural brick. Here's our first brick. And we, since no one had used this material for large-scale exterior architecture before, we had to do a lot of material testing. So here's the testing at a strength of materials lab at Columbia University. Here we're compressing a brick to 100,000 pounds. It won't have to withstand that in the building. But testing single bricks, small assemblies of bricks, because when we're working with the new material, you know, we have a lot of things to figure out. And we used this approach. We used as fuel for this research the competition that Jasmine mentioned for MoMA PS1. So this is the courtyard of MoMA PS1. Where we had 3 weeks to build our structure after kind of convincing people that this was a good idea to build the structure in the courtyard. And here, as it was still an experiment, we had to add other ingredients to the equation, to the experiment. And we had Columbia University architecture students who knew a lot about architecture and form and computation, working side by side with New York City brick masons who know a lot about stacking objects. Neither one alone had ever made something out of this strange new material before, but they kind of worked together in a creative ecosystem to problem solve in real time on site. And I should note that everyone was fairly paid who worked on this project, because that has been an issue before in this competition. In the end, we built this structure you see here, and this photo in particular shows it in the context of the glass and steel buildings of Manhattan in the background there, and also in the context of the red clay brick building of MoMA PS1. For us, this was not only a fun experiment, although very stressful, but also a medium scale test of this new material and this new possibility for architecture. So in other words, it was about 40 feet tall, more than one story, and it involved about 10,000 bricks, more than just a handful of things on our desks. In addition to testing the technical performance of the material, we also wanted to test what we could maybe consider the atmospheric potential of the material. What would it be like to be inside a structure made of these kind of bricks? What would be the patterns of light and shadow and texture? What would it smell like? What would it feel like? The ultimate test for any of these projects, and unfortunately this program has been discontinued for the moment at PS1, but it existed for about 15 years, and the ultimate test of every single one was its ability to host a good party. Because every Saturday of the summer, 5,000 people stream into this courtyard and listen to experimental electronic music. This was the first Saturday of our summer, and it was thrilling but also terrifying to have people walking inside of our experimental structure, scratching at it, even climbing it, trying to climb it. And when night fell, we breathed a sigh of relief. But it was actually entirely fitting because, as you can kind of sense probably by what I've shown so far, it was important to test this out in society, out in culture, out in public, a version of public, as opposed to testing it just, you know, in the world of academic papers or on the lab bench or in the fenced-off proprietary corner of a construction yard. You know, we wanted to test this out in the world. We wanted to see what people said about it, how they felt about it, what it struck someone who knew nothing about this material or sustainability or architecture for that matter. At the end of the summer, contrary to most buildings or pavilions, we were a little careful about taking it down. And we took the bricks, crumbled them into smaller pieces, combined them with a broader ecosystem of living organisms, more specifically bacteria and worms, in a compost site. And then in just about 60 days, all of the physical stuff of that building, all of the matter, returned to soil through composting, which we in turn gave to New York City tree planting and even community gardens. And another way of thinking about that is that here's my son, 8 years old at the time. taking a bite of one of these bricks. I should say I also took a bite. I didn't just make him do the test, but it's showing that this is a non-toxic enough material that you can eat it.
You took a bite first.
I took a bite first. He said it tasted like oatmeal. So, like many of our projects, this is very, a weird experimental idea, an unusual material, but we're looking for broader ideas that might be generalizable to other materials, other approaches. And here we were thinking that, maybe we could, as architects and designers, think as much about designing to disappear as we typically think about designing to appear. Now, like I described before, often, but not always, our research projects lead to new lines of inquiry and sometimes to new projects. So, for example, with this project Hi-Fi that I just showed, our bricks were made with a living organism, but then they were dried out, so they became dead, inert, and predictable like every other building material. But we always had this idea, and we even thought we might do it for the PS1 competition, that what if you kept the bricks alive? What if you didn't dry them out? What would happen with a material, a brick, that was literally living? And this was an idea that we had had for a while. We didn't explore it at PS1, but we found a different opportunity to explore it in a project a couple of years later for the Pompidou Center. And our idea here was that we keep the bricks alive, and then maybe we could do things like have the material heal itself if it got damaged, or we could have the material bind to itself over time based on certain conditions. And we realized that we could place different bricks next to each other, these living bricks, while they were still growing and alive, and they would literally fuse together. And we started calling this process biowelding, a kind of biological gluing together. And it was really interesting and exciting to us because you can almost imagine that then you have brick and mortar in the same object, an object that is a dynamic system, like we're talking about buildings, just like a building can be a dynamic system. This is kind of lo-fi time-lapse of how it worked in one of our first tests, and you can see over a couple of days these objects like literally fusing together. There's a more close-up view. And we did a number of different experiments at different scales. Here's one, like the units, the bricks are kind of bucket-sized and shaped, so this is about 4 feet tall. We just like dump these together in a cardboard box and they fuse themselves together. And this gave us a lot of ideas, like what could we create out of a material that could do this? And one of the things that we were also thinking about at the time was a different kind of material system or material property that's sometimes called material jamming. So jamming is an idea of like you have objects or units of material. So for example, units of sand, grains of sand. And depending on the size and shape and the way you work with those units, they can create really different forms and formations. So this is just a random photo of a pile of sand, but I'm using it to show that if the grains of sand were really spherical, you'd create a pretty shallow mound as you just poured them randomly onto the desk. If the grains of sand were more angular, then it would create potentially a steeper mound. If somehow you could create grains of sand like a tetrapod, like a forked shape of grain, then you could get even steeper mounds and do even more interesting things, as the friction of the object and the shape of the object creates certain physical properties. So this is sometimes studied in grain silos. These are just some diagrams of grain silos. And there's a whole body of research about how to avoid clogging of a grain silo, because the grains are, objects, and they sometimes get clogged as they're, getting poured. And we thought, if you look at the right, wow, a clog actually could be a really interesting way to create a type of bottom-up architectural form. In other words, maybe we could purposely create a clog with the right kind of unit, the right material, the right geometry of unit, the right formwork, and we did a whole bunch of experiments. So these are experiments with a different size and different shape and even different material than we intended to use. but they gave us some really interesting ideas. So we're pouring these units in a formwork. We're changing the angles of the slopes they're dropping on. We're changing where we drop the units, whether we drop it only once from the center or twice from two sides, and just looking for interesting possibilities in a really open-ended way. And eventually we found some formations that we thought were pretty interesting. It seemed to be based on some of these properties that we could control, but also some self-assembly or self-aggregation logic. And that one in particular we liked. Then we went to a different scale with a different material, but similarly trying to draw on, there's our failed experiment, trying to draw on some of the lessons from the different scale, different material. And there's a certain kind of size and shape of the formwork in relation to the size and shape of the unit, and the size and shape of the slope of those surfaces that it's pouring on. And we were able to get a certain kind of aggregation of units based on material jamming. And so we had these two things that we knew how to partially control, material jamming and biowelding. And we had an exhibit that we had agreed to produce. And so we went on site with having done some scale experiments, but our full-scale installation was also itself an experiment. So we were trying to create this project for the Pompidou Center about a 12-foot high arch made of these two processes. So this is just a kind of sense of different steps. So this is like just a scaled-up version of that quarter-scale mock-up that I was showing before. We created a formwork for the units. These are mycelium bricks. And we put it in the formwork, kind of packed it down. And the two things that we hoped would happen are shown here. The first was we removed the bottom, basically the plug at the bottom of the funnel. And ideally, there are going to be some loose units at the bottom that you can just kind of shake out pretty easily, and some more kind of densely packed units that create an arch. So far so good. It was kind of creating an arch in a form that we kind of controlled, but kind of didn't control. The second big test was after the biowelding and the jamming happened, we were going to remove the formwork entirely. And the object was supposed to stay together. We were supposed to have the mortar between the bricks, and the object was supposed to be, a single object rather than an assembly of bricks. And we, again, agreed to decide that the experiment seemed to work. So this was just, a test at a certain scale. But it was something that we thought, held some promise. And just by even looking at it, gave us some other ideas, some possibilities, some ways to challenge the way we normally think of architecture and detailing and assembly and control of a dynamic system. Now, number 4 is actually closely related, and it's a work in progress, but I think it's important for me to show it. It's something that we're working on right now, and maybe one way to introduce it is that about 9 years ago, when we made the hi-fi exhibit that I showed, the question I got most frequently was, yeah, but when is this going to be in the real world? And it was a question that was both annoying, but also, I understood, important. And I would often answer, well, it's challenging, but I think within 10 years, we're going to see this in the real world. And I didn't have any idea that I would be working on this or be involved in it, but I knew enough about the material to be pretty confident that it was possible, that somebody could do this. And now, 10 years later, I'm part of a broad team of collaborators, led in part by a creative team at Autodesk Research that will bring this to life, that will bring this material into a real-world project next year. And so I'm just going to show a little bit about it. It's still a work in progress, but this is the Phoenix project. It's a 300-unit affordable housing development in West Oakland. Here is the vacant lot. And here is what is planned for the site. Even though it's kind of a project that's still a work in progress, I wanted to show now this trajectory because it represents what I think is important about finding a path from experimental research to scaling up and having an impact in the world. So overall, this project is what a lot of the collaborators are thinking of as an innovation village for new approaches to address the housing crisis. And so more specifically, we're exploring different ways that we could try to reduce the time, cost, and carbon in the project, addressing all of these three important components simultaneously. So for time, this project, Phoenix, is going to be about 50% less than a typical project. For cost, it's going to be about 40% less. In both cases, this is mainly due to factory construction, also to digital workflows and reusable design intelligence, and to some degree through some government funding. For carbon, this project we think is going to be about 60% less than a typical project. Now, part of this is due to California regulation and government, because it's going to be an all-electric building, like all new buildings have to be of this size. But there are also carbon reductions due to factory construction, and there are other parts of it that are due to some of the more experimental things we're doing on the project, including reducing operational carbon through natural ventilation, and reducing embodied carbon through an innovative facade system, and I'll mainly focus on the facade system. But just to give you a sense of the context, the approach starts with these prefabricated modules. This is factory construction that I was talking about. And they're being made by Factory OS, which is a modular housing construction company in the Bay Area. And for the past few years, they've been working on what we could maybe call bringing physical world innovation into the ecosystem of making affordable housing. And we've also been combining with that physical world innovation, a kind of digital world innovation. So trying to manage all of the complexity and data of a project through multi-scale generative design. So trying to look simultaneously at all of the factors for the site, and all of the factors for the building, and all of the factors for the unit, and all of the factors for a single panel. So can we take all of those factors together into account and design them together? Another way of thinking about it is that we're aiming to simultaneously promote cost, carbon, and community. So these are three categories that we think are critical for the project, and we're looking at all of them in the same time, at the same time. So to do this, in part, we developed some kind of building blocks, including some building blocks for sequestering carbon in both the building facade and in the landscape, and building blocks for promoting community in public spaces and private spaces. And now I'm going to zoom into the material stuff. So this is where the scaling up of the biomaterials comes in. So for this project, we developed what we're thinking of as a carbon negative facade system that we think will be useful for this project, but also generalizable to other projects. We're thinking of this as a drop-in material solution. So in other words, it's a material that we think can work with today's building codes, today's certification schemes, today's construction methods and contractors. So it's almost the other end of the spectrum than the installation for the Pompidou Center. That's like, how far out could we get? What could this be in another 10 years or in 30 years? How might we be making sustainable architecture? This is, how can we move the needle today? You know, what can we get in a building that's going under construction tomorrow? And what we ended up working with was combining two materials and two material systems. So this is a composite system for a facade made of a shell of fiber reinforced polymer and a core of mycelium, the same mycelium material in the past two projects. And we think this gives us the best durability and high performance from the FRP, and the best of low carbon and sustainability from the mycelium material. So zooming in a little bit, this is how we think we can make a facade for a building that's going under construction next year, and make it carbon negative. So I won't go into the details, but if you look on the left, that's how we make this kind of facades today. Each layer has a little bit of pink, and each pink is a little bit of carbon. So every single layer, the waterproofing, the insulation, the structure has a little bit of carbon. But some materials have less, require less carbon to produce than they absorb during their process of production. I know that sounds confusing. Think of wood. You know, a tree absorbs carbon from the air while it grows. And if you can take that tree and convert it into a building block with very little carbon, and that's important, and replant the tree, then you have something that net has taken carbon out of it. And mycelium material could be like this too, because of the agricultural waste. This is material that would be either burned or composted and go back into carbon dioxide in the air. If you can trap that agricultural waste in a building material or in something that's going to lock it in for 100 years, then you could be net removing carbon. So that's the green layer. And by tuning the pink layers and the green layers, maybe you can get to an equation where you have net less carbon in the material than went into the material. At the same time, this material has the potential to have a lot of other layers of performance. So it can have acoustic performance, it can have structural performance, waterproofing performance, fire resistance. We can make it in big panels, which can reduce construction time. So we're working with all of the practical demands of making a building right now in today's conditions. And here's a different view of what we could think of as the traditional FRP system. If you've ever seen the facade of the SF MoMA, this is this kind of the addition. This is the kind of system used for that. It's an FRP sandwich panel, and we're replacing what's typically the middle of the sandwich, an EPS foam, with the mycelium material. So this required us to make a different version of mycelium material than we had used before. It has to be stronger. It has to work particularly in shear. It has to be directional. And so here are a number of different tests where we're trying to coax the material into the living material, the uncontrollable material, into conforming in the way that we needed it to perform. So this involved a lot of months and months, actually, of physical testing, digital simulation, revisions, different partners doing different things. And in the end, we were able to get hit a performance target that would allow us to use this in today's buildings with today's certifications, building codes, et cetera. I won't summarize this chart, but on the right, you can see those green numbers are basically showing that we were able to get 8 times the shear modulus of EPS foam. And originally, our target was just to get 1.5 times that. We've also been working through other material performance tests to make this real. Here is the so-called E84 fire test, where you create a 24-foot long section of the real material assembly and set it on fire for an hour, basically. And this material system basically received a Class A fire rating. It's basically ready to go in buildings in California, residential buildings under 40 feet tall. We did other kinds of testing. This is basically just figuring out the logistics of how to install and detail some of the parts, which ones to install on site, which ones to install in the factory, how would all the attachment clips work. We workshopped the design of the facade with geometry that is intended to create shading, also acoustic buffering, also thickness to store the sequestered carbon. Here's the manufacturing of some of our exact materials. So this is similar to the manufacturing process that I showed earlier for a previous project, but it's an updated version that is engineered to create a stronger material. We had to do a lot of digital testing. Here's a structural performance analysis of a 36-foot long panel under various forces that it will have to resist in the building. And finally, this is just from last week. Here's the fabrication of the first mega panel, 36-foot long panel made of the fiber reinforced polymer, basically fiberglass, and the mycelium core. So here's some of the units. These are stronger than the typical units. Here's some of the other ingredients, the fiberglass. And you kind of probably see where I'm going with this. There's some trade-offs here. We're using some non-organic, non-sustainable materials because they're available now, because they will allow us to get the biomaterial certified into the buildings in the next year. And I think it's a really important discussion for architecture to have. Like, what is the balance of our collective effort on drop-in solutions for the next 10 years versus reimagining the whole system? Here's one of the panels from just a couple days ago that's waiting for installation on the housing module. And while this may not look super transformational, while the mycelium material and the carbon impact may eventually be invisible, actually, and while developing this new material system has required challenging work, messy work, we think this process of moving from demonstration project to scale up is critical, and we think it needs more investment, more creativity, and more emphasis in both school and practice. To put it in a little context, here's a rough heat map comparison of the embodied carbon in different components of a building. The foundation, the red, the kind of hot spots, the worst side. Hard to get a foundation with low embodied carbon. But by the time you get to the envelope on the right-hand side, there's some good options. Even hardy board or brick veneer are okay. They're medium, yellow is medium. Wood is very good, but it can also be very expensive, and it can have a lot of maintenance required, and the resources required to make it can be challenging. So what we're hoping is our two green boxes on the right there are ways that we're thinking we can add to the palette of materials available to make low carbon choices for a facade. Okay, so finally, the fifth approach that I'm going to show is what I sometimes call open sourcing the building. So this is a project that explores our vision for living, breathing architecture in a slightly different way. This is called the Embodied Computation Lab at Princeton University. It's a building for the next generation of research on things like robotics and sensors, and everywhere that computation meets the physical environment and becomes embodied computation. The building is located near the athletic fields and the new chemistry building. Historically, this has been a site of great architectural experimentation. Here's Buckminster Fuller making his first geosphere with students on this exact site in one of the former buildings. The program involved multiple uses, similar to stuff that I'm sure you have here, from teaching to fabricating to testing full scale. But also the program really called for something interesting, which was we had to design for both the known research of today and the known equipment of today, and also the unknown research of tomorrow, unknown equipment of tomorrow. So how do you design for both things at once? And our concept was to create a kind of open source building. So like open source software, the idea was that this could be like designed to be released as a version 1. It's fully functional, but also very much designed to be updated and changed over time by multiple authors. And this worked in several ways. First, the building was deliberately incomplete. The left-hand side is like a normal enclosed building, but the right-hand side is just an incomplete frame designed to be filled in over time. Second, the building has many swappable modules and systems like radiant heat that on day 1 is getting the heat source from the building next door. But with the kind of plug-and-play system, you can flip a switch and then get the heat from a geothermal well that the researchers are planning to build. The building is also rewritable over time. So many of the decisions were about things that could be changed, cut, revised, added to. What were systems and materials that could allow that? And in that way, we hope that just as maybe a biologist would use a microscope as a research instrument, architects and engineers could use a building, a real-world building, as a research instrument to study and adapt and experiment. And fourth, the building is really designed to learn over time. So like living organisms, it's continually processing information, including high-resolution data from a lot of sensors for things like heat, temperature, light, occupation, and it has a number of ways that it can evolve based on this. There are also some unique and important sustainability features. There's a floor that's being used for radiant heating and also radiant cooling. Here's a view of that in the winter, where the heat is yet another one of these invisible but important features of architecture that I'm describing. The structure is made of glulam or engineered timber. And the facade is made of repurposed scaffolding boards. So these are boards that are used on every construction site in New York City. They're typically used for about a year and then literally thrown in the landfill because it's easier to create a rule of thumb about material use than actually check it or inspect it or have a finer grain of analysis. So we took these scaffolding boards, which were almost free and pretty much destined to be in a landfill and carbon go back into the air, and tried to give it a new life in a building facade. And we also thought that this material had a lot of interesting properties and some unlike other materials. So these kind of weathered scaffolding boards were a biomaterial that was non-uniform. And we developed a hypothesis that this weathered wood could actually be a benefit. It could actually have performance benefits for thermal insulation, trapping small pockets of air and acting as like a jacket for the building, or even hydro performance benefits through shedding water off the material. And we also knew that the building itself had different zones that required different performance. So this is a solar analysis of just one of the facades of the building. You can see that over the years, some is more shaded than others. So we really engaged a mini design challenge for this project, which was we had thousands of boards with different properties, these salvage scaffolding boards. And the challenge was which board to arrange with which properties on which position of the facade to basically use the variation of the biomaterial as a benefit, not as a drawback. I won't go into this in detail, but we used some computational techniques here to analyze the unique properties of each board. We took pictures of the boards and we basically decided how we were going to use each board based on a kind of analysis of each board's unique properties. So the way this worked, just in summary, was we created a bunch of photographs of boards, asked humans to look at a small set of these photographs and basically classify each photo. You looked at a photo and you either clicked the button not with a KN or not with an N. You're just saying, like, does this photo have a not or not? And after the humans basically classified a few hundred of these pictures, we used trained a computer system to classify the remaining thousands and thousands of pictures. Here's the computation kind of guessing at where the knots were in a photo that had never been seen by a human. And one thing that was very interesting to us, this is just a different view of it, the computer kind of learning from left to right where it thinks the knot is. The computer was able to look at a new photo and not only figure out where the knot, not only figure out if it had a knot, but also where the knot was located, even though the human had never said anything about the size of the knot or the location of the knot. So this is the technology, I mean, it's well known to us now, that's being used for various things on the internet, for various things about financial trading, et cetera. Can we use this for a problem like working with difficult architectural materials? Then we did some custom fabrication in terms of sandblasting to basically create the types of micro contours in the wood that we wanted just at the right zones. We used a kind of custom machine, some custom software. And really, again, the bigger idea here was that we could explore a different approach to materials that maybe celebrates variation and non-uniformity rather than trying to erase it, that sees how each board came from a specific place, from a specific tree that grew in specific conditions and formed in specific ways, and how we might ultimately overturn the default rules of thumb and the lowest common denominator approach that you typically have to architecture materials. More fundamentally, this allowed us to think of basically any building as a temporary formulation of materials, energy, and labor that's connected to other formulations before and after the life of that specific building. Here's how it registers at different scales, the 3D form of a single board, zooming out some of the boards installed on the building, offering this kind of unique but also familiar appearance. The facade itself is an example of embodied computation of the state of this kind of machine learning with some false positives and false negatives, some promise and risks. Here's the building kind of in action with the gantry crane that goes from inside to the outside with two large hangar doors on either side of the building that open up and allow projects and materials to flow from one into the other and adapt to different research scenarios and some of the unknown future. And basically the dynamic and adaptive structure for this building, we think, proposes an alternative to buildings that are static and driven by form or aesthetic signature alone. Overall, the building maybe suggests a hybrid new design approach that's both high-tech and low-tech, familiar and new, functional and aesthetic, digital and biological. And in the end, while the building itself is meant to be an open-ended research project and a reusable model for other architecture projects in the future, it's also a specific and tangible demonstration of design, of atmosphere, of the experience of space, and of what it might feel like in one version to live in a strange new architecture designed for both humans and machines in the context of the natural environment with the vision for a new form of living architecture. Thank you.
I think we have a little time. I know you guys have to go to class at 1:30, but we'd like to take questions. I think if we can from the students. Before you leave, any questions for David? I know you have them. Yes, one in the back.
I had a question about the biowelding. Is there a natural stop when the biowelding, or would there have to be an injection?
Yeah, that's a good question. So for the biowelding, I'm going to repeat the question. For the biowelding, is there like a natural stopping point or how do you control it? It's a little complicated, but there is a kind of natural limit to how much it will grow. So it's not like it's continually expanding. So press a button or stop it. But that said, it's still potentially a living dynamic system until you dry it out. So the drying could be natural, just through air. It could be enhanced through sun exposure or heating. And so that's, I think, something that would have to be tuned by the requirements or desires of the designer, because it's still a little bit uncontrollable process. I mean, just to give you a sense, I know it sounds funny, but one thing that might happen if you didn't dry out the material is first it would fuse together. It would kind of eat up all the available nutrients. And then at a certain point, when there were no nutrients left, but it generally has enough nutrients to bind to itself, then it might start sprouting mushrooms. And that could come with benefits, but also drawbacks. And so it's a kind of process that you can tune a little bit through different things that you would do to the material, but it's still a little bit beyond control. Now, I want to mention one other thing. When we worked on this mycelium project, almost 10 years ago, one of the things that we found fascinating was that the materials company 3M, 3M from Post-its and Scotch tape, they know a lot about materials, or at least chemically derived materials. They, at the time, had invested in mycelium because they thought that mycelium had the potential to be a materials platform like plastics. And my interpretation of that was, plastics can be like clothing, they can be fabric, they can be hard and rigid, they can be dense, they can be a foam, they can be lightweight, transparent, many things, right? And mycelium potentially could be that too. There are probably millions of species of fungi, and they have different properties, and they grow at different rates, and they produce slightly different things. And so I think we're just at the tip of the iceberg of how we could use this material in different ways. So the uncontrollability that I'm describing is just like early exploration, and potentially you could start engineering things really specifically.
Other questions? Yes.
Are there hypothetical alternatives to fiberglass for the FRP project?
That is a great question. We've been looking into that a little bit. There are probably none that are certified for next year. I keep mentioning that. But there's some bioresins that you could use, to replace the epoxy resin or the petroleum-derived resin. And there are some fibers that could be used too. Natural fibers, maybe flax fibers, maybe basalt fibers. So that's more like a mineral fiber. So in short, there are people doing really interesting work on it. It hasn't yet got that kind of certification, but I think it's coming. And I really appreciate the question because that's the next step. I think that's why it's okay to use the drop-in now, because we got to do something now, and we got to do something in 5 years, we got to do something in 20 years. And having the big picture in mind is really important.
one here in the front.
What's the longest time period that you've had this mycelium structure up? And if so, have you seen any structural issues over time?
Great question. The longest time span we've had mycelium structure up. So I have some bricks on my desk that are 10 years old, and they're just the same as 10 years ago. And actually, before we, in order to try to win that PS1 competition, we did what's called accelerated aging testing. We took a brick, we sent it up to a lab, and they simulated 3 years worth of New York City summer in a row. Like rain, heating, the temperature, humidity, no snow, because we were just there that summer. And then they do this, pretty scientific testing, the mechanical properties before the testing, middle way. And it's the mechanical properties were exactly the same after 3 years. Now, exterior rated structural performance, just one summer. That's the longest thing that we have had installed, and that also that I know of. But I'm also absolutely confident that this drop-in solution, for all of its drawbacks, is going to last for 100 years. I mean, it's basically going on the building with a normal contractor, with a normal insurance policy, with normal building code certification that basically guarantees a 50-year building. So if you enclose it, in other words, it could last as long as styrofoam. I mean, hopefully not as long as styrofoam, but as long as you want it to last. Because that's the other thing about mycelium. It's not just going to fall apart over time. It biodegrades by triggering the biodegradation, by crumbling it into smaller pieces, by putting it in the compost site. And if you just keep it on your desk, it could probably be the same.
Other question?
So I guess in looking at biowelding and biofabrication, sort of more natural, organically driven materials, for you guys, is that something to where, I don't know, you have biologists working with you, or how does the architect relate to almost the organics and the nature, I guess?
Yeah, that's a good question, because it also relates a little bit to our approach as a studio and just a kind of methodology of research. We tend to work with a lot of different people, and we are not afraid to ask questions, not afraid to ask naive or dumb questions, not afraid to approach a biologist or someone else and say, hey, what about this idea? And we do that with biologists, but sometimes with structural engineers. We work with artists, with a range of different disciplines. I think two things about it. One, we need that expertise, but I've learned over time that you have the most success when you can find the common ground, or even just find the common language. So in other words, I actually still to this day have some computer scientist friends, and I'm no computer scientist, even though we try to do work with computation. And we're still kind of struggling. We have a great amount of goodwill. We've actually done a little bit of work together. But he's continually asking me questions that maybe I could answer, but they're not interesting. And I'm continually asking him questions that he can answer that aren't interesting to him. And the trick is finding that middle ground where we're looking at something that's interesting to both of us. And I think that's a little hit or miss. It's trial and error. But also there are ways to frame things. And also there's learning enough about a field to try to ask a question that might be interesting. So the second approach is I'm actually going to borrow this from a lecture that I heard, I think when I was a student, from Sheila Kennedy, who is an architect in Boston, does a lot of material research, has been kind of model for me anyways. And someone asked her a question about a similar question, how do you do materials research? How do you get expertise when you're doing something really technical? And she said, it's important to me to know just enough to be dangerous. So, I think part of that is, you got to do your homework, but you don't have to necessarily become a programmer, become a synthetic biologist. You have to know enough to ask the right questions, to seem like you're asking for more than a favor, that you're asking about something that is something important under there, something at stake.
We have two here. We'll start with Jeff and then Mark.
Sure. Thank you very much. been working with students for several years on FRP structures, especially for housing. So it was really fun seeing the work you've been doing. Ever since Clark Foam, the surfboard blanks manufacturer, shut down in Southern California, there was this whole panic about what the core materials would be and what to do. And we've been looking at some different biocore materials, and mycelium seems really promising. I've had a number of students actually reference some mycelium research and work on that. So I would be very interested to see where we're going to go with that. And one of the things I was curious about in this testing that you did as a facade system, I'm a friend of Bill Chrysler's. I'm sure you've talked to him about work he's done. I'm wondering about that movement from facade system to structural system. You kind of acknowledged that in the PS1 thing with the primary structure steel and whatever. It's something that obviously we'd all like to see happen eventually. Is there any thought with the panels that they might become something like a primary structural?
Yeah, in short, yes. So I think but actually really great to know about your research as well. I think we connected about that. But and I think there are probably a lot of other biomaterials that can be a core.
Yes.
So our first step, just practically speaking, because we're kind of going back and forth between like what would be a valuable problem to solve that's generalizable, and like how do we get this in the building that's already on schedule. So the next step for us is to make sure that these panels that we're making can be structural enough to tie together the units. So you stack these modules of housing, and then there still needs to be some kind of structural connection, especially lateral. And it's hard to solve because like you can't solve that in the factory. It don't make sense when you're on site. And so now we're working on getting the composite sandwich, the fiberglass and mycelium, to be strong enough to provide that structural shear connection between units. And we're pretty confident it can do that, but we still have a little bit of engineering of the strength of the material. I think the next step would be more something like a SIP replacement, like a structural insulation. Like you don't need the studs because you don't have the whole thing.
Yeah.
And I think it could do that. I mean, the combination of the stuff we've done with just load-bearing bricks out of this material and what we're doing now with the panelized version, I'm pretty confident it could do that. And it could be done like, there's some great research in that area. Like BAMCore is a company that's making these kind of very sustainable or carbon negative structural panels that are replacement for SIPs.
I've been talking to Carbon Composites One about that. Chat after anyway. It's delightful to see all that. Really
great. Yeah. Thanks for the question.
I think, Mark?
I have one question. It's actually more about the whole content. Sort of zoom way out. Started the lecture with the statement that the embodied energy is increasing as a portion of the total energy usage of the building. It sounded kind of bad because embodied energy is increasing, but I would look at it the other way for just a moment. I think what we're seeing is success in reducing the operating energy side of the equation. One of the reasons that you have become important now with this is that we've had some success. After Doris, after X years of teaching, we've had some success getting students to consider this stuff. And in fact, we're having success in this. We paint the bad picture. We need to continue working, but I also want to paint the good.
I totally agree. Thank you for mentioning that. Right. I was only talking about the proportion. I wasn't talking about the total amount. And I could go on and on. You all probably know some version of this, but there's actually a real success story that the total carbon in U.S. buildings has gone down by something like 20% in the same about 20 years that the total number of buildings, the total floor area has gone up by 30%. So we're finally separating the amount of carbon from the total amount of buildings. So I agree, it's total success, although probably part of it is architects' awareness, but part of it is just renewable energy, which is advancing exponentially. But one thing that still keeps me up at night, because I agree, we need to celebrate success, but also work on the problem, is that, you know, we're on track to have 2 billion more people in the next 30 years. The built environment is scheduled to double in the next 30 years. So even though we've squeezed out, you know, a lot of the carbon, and that's great, we have a lot more to squeeze out because we have these goals of 2030, it's got to be 50% of what it is now. 2050, it's got to be 0 total embodied and operational combined. So we need embodied.
So on that note, we're hitting 1:30, a little past 1:30. I know you guys have to go to class. Thank you all for coming. Thank you, David, for being here.